Section 6.1, part 2. So again, we'll scroll back up here to the top. We're doing our scatter plots, our correlation, and our fitted lines. Okay, so just quick review. So far, we've talked about the 3 different types of correlation: negative, positive, or no correlation. We've talked about that weak or strong correlation. And we've also talked about that correlation coefficient. The closer to 1 or -1 it is, the better it fits the data points. Okay, so now we need to talk about the difference between correlation and causation. Okay, so one of the main errors when interpreting bivariate data is to observe correlation and assume that it means causation. Okay, correlation again just means that as one goes up, the other goes up, or as one goes up, the other goes down. Okay, so again, that correlation basically just means a change in one variable change in one variable also shows a change in the other. So as one goes up, the other goes up, or as one goes down, the other goes down. Whereas causation means the one variable causes it to happen. Causes the other one to change. Okay. Correlation, and instead of versus, does not imply causation, meaning just because one thing goes up as the other goes up does not mean it's causing that to happen. Okay, so correlation does not imply causation. If you notice the word cause, the word cause is in there. It causes that other thing to go up. So we're going to look at a few examples, and we're going to do some more examples. We'll kind of have a bit of class discussion on and off about this throughout the year, talking about that correlation versus causation. So here we're going to look at 3 different examples where we have correlation. All of these have some correlation, but some of them have causation and some of them don't. Correlation and causation are really 2 different things. Correlation is just looking, hey, as one goes up, does the other? Or as one goes down, does the other? Or as one goes up, does the other go down? What is it doing? So here, what happens to the height of a child as his or her age increases? Well, usually, as you get older, you get taller. So what happens to a child's height? The height gets larger. Height also increases, which tells us that this is going to be a strong positive correlation. The height of a child and the age of that child have a strong positive correlation. Do you think that the correlation is due to causation? Is the child getting older causing them to get taller? Okay, thought? Yes. What happens as you get older? You grow. Okay, so as you get older, you grow. Okay, as the child gets older, they grow. Okay, so your getting older is causing you to grow. Now, is it going to be nice and perfectly linear? No. It doesn't necessarily, like, you're not going to grow. Every kid doesn't grow 3 inches every year. Okay, you might not grow hardly at all for a few years, and a couple of years later, you grow a lot. But it does have a strong positive correlation, because if I graph age to as a kid gets older, yes, they're going to go ahead and get taller. And there is causation. As a child gets older, they grow because you're developing into an adult. You're growing into an adult. Now, after a certain age, that's going to stop. Again, we're talking about a child here. Okay, so as you get to adulthood, of course, that will stop. All right, so here we have the next situation. It says the number of absences a student has and the student's grade point average have a strong, they tell us it has a strong negative correlation. So basically what that's telling me is if I look at a graph and over here is the number of absences and over here is your GPA, your grade point average, the more absences you have, the lower your GPA is going to get. It has a strong negative correlation. So what happens to the grade point average as the number of absences increase? The GPA is going to go down. Is going to go down. Yes, that GPA is going to go down because it has that strong negative correlation. As absences go up, GPA goes down. Do you think that the correlation is due to causation? Does being gone a lot affect your grades? Yeah, yes. Missed class time means missed instruction or missed lessons. So what happens? Get behind, grades go down. Okay, there is always exceptions to the rule. Okay, what we mean by that is a good student who doesn't hardly miss and who's here all the time and whose GPA is good, if they suddenly are to have to be gone for like 3 weeks, chances are they've created those good habits. They're going to keep their grade up, right? They're going to keep doing stuff outside of school. But generally, as you miss more class time, you miss the lessons, you get farther behind in your grades, what happens is it snowballs, right? You get way behind and then you're stuck digging yourself out. So yes, there is causation here. So do you think that the correlation is due to causation? Yes. Missed class time means missed lessons, so you get behind and your grades go down. All right, here's the next one. Here, the number of people jogging and the number of people biking outdoors have a strong positive correlation. Okay, so again, if I was to graph, and here I have the bikers. Oh, this would be the joggers. The number of people jogging and the number of people biking have a strong positive correlation, meaning it's going to go up. As the number of joggers increases, the number of bikers is also going to increase as well. What happens to the number of joggers is the number of people biking increasing. It also increases. It also increases because there's that positive correlation. Do you think that the correlation is due to causation? Is the number of people jogging causing there to be more bikers? I would say no. No. There is possibly a different variable. At play here. Okay. What I mean by that is what might cause the number of people out jogging and biking to go up that would cause both of them to go up. Okay. Okay, that's this last question. Explain how another variable could have a causal relationship with each of the original two variables. I don't know about you, but I'm much more likely to go outside and do stuff if the weather is nice. I'm thinking weather conditions, or more specifically, aka temperature. Temperature would have a causal relationship. Would have a causal relationship with both, with bikers, with joggers and bikers. Okay, the reason as the number of joggers goes up, the number of bikers go up is probably because it's getting warmer. As the temperature goes up, there's more joggers out, which also means there's more bikers out. People who enjoy being outside, whether they run or they bike, are more likely to be outside because the temperature. So I think our other variable at play here is the temperature. So do you think there's correlation due to causation? No. The number of joggers being out is not causing the number of bikers to be out. It's just the reason, the thing that is causing the joggers to be out is also the thing that's causing the bikers to be out. Okay. So causation versus correlation. Okay. All right, now we're going to actually create a line of fit. Okay. So a line of fit. What is a line of fit? Basically, a line of fit is a linear equation that fits the data. And I'm going to put quotes around that. It's a linear equation that fits the data. It fits it as close as possible. And so for this section, we're really just going to be eyeballing it. We're going to try to get a line as close to as many points as possible. Okay, so here's a scatter plot for our hot cocoa sales. If you don't remember, it was from the last section. It was from the first section here. We have this hot cocoa data right here. So we have this hot cocoa data right here. Okay, so we created a scatter plot for it right here. Okay, and we kind of drew in a bit of a line of fit. Now we're going to do create a line of fit. We're going to draw it in, and we're also going to create an equation for it. Okay, so first I have to create my line. So first what I'm going to do is I'm going to grab my ruler. There's my ruler. So I'm going to grab my ruler and I'm going to bring it up here, and I want to get it as close, and it doesn't actually have to hit my points, as close to as many points as possible. Okay, so like I wouldn't pick, let's say these two. Because if I notice all of these points up here, all of these points up here are all above the line. I don't want them all to be above. I also don't want them all to be below. Meaning I wouldn't pick, let's say, this one. Because if you notice, we have all of those points under there that are below. All those points under there that are below. We want an equal number above and below, and we want them equally spaced. So I'm going to shoot for somewhere in the middle here. Let's see here. This one might not be so bad. I've got, looks like 1, 2, 3-ish points above, 1, 2, 3, 4, 5 points below. So maybe we should go about that. 1, 2, 3, 4 points above, 1, 2, 3, 4 points below. That one looks pretty good. And then we draw in our line. Okay, let's go ahead and move the ruler. So there's my line. Okay, so now we need to write an equation for that line. So to write an equation for that line, you need 2 points to write an equation for that line. So I'm going to go ahead, I'm going to pick 2 points. Now the 2 points don't necessarily have to be data points. Like they don't have to be the green points. I can use any 2 points that are on this red line. Okay, so first off, let's say this one data point here is right on the line. So we're going to use that one. And that would be the data point just slightly more than 40. So is that the 42,265 point? So this one right here is the point 42,265 is that one right there. So we'll use that point. And then I need another point, but again, it doesn't have to be a point necessarily. I think I'm going to use this one right here. It's the point 80, and it looks like it's almost smack dab here at, what are we, 20, 40, 60. What are we counting there? What, at 50? Halfway between 0 and 100. So 80, 50. I think is that point that we'll use. Again, that wasn't a data point. Like we don't have the data point 80, 50, but that's okay. We just need 2 points on the line. So now I need to write the equation. Y minus y1 equals mx minus x1. First, I need the slope. Slope is that change in y over change in x. So I'm going to subtract my y values. 265 minus 50 all over 42 minus 80. Okay, so let's grab my calculator. So we're going to take parentheses. I'm going to do it all in one step. 265 minus 50 divided by 42 minus 80 gives me that. Math, enter, enter, which is negative 215 over 38. Okay, so we'll go ahead and have that be our slope. Not pretty, but it'll work. Negative 215 over 38. Oh, sorry. Go away. Okay, so there's my slope. And then I need an x1, y1. So I think I'm going to use, I don't know, these numbers are smaller. Let's use the 80 and the 50. So we'll have y minus my y coordinate, which is 50, equals negative 215 over 38, x minus my x coordinate, which is 80. Okay, so now I'm going to distribute this through. So y minus 50 equals negative 215 divided by 38x, negative 215 divided by 38 times negative 80. So multiply that times negative 80 gets me positive that, which is 8,600 over 19. And then we need to add 50 to both sides. Okay, so here's my equation. Y equals negative 215 over 38x plus, now I need to take that what I had and add 50. Woo! Which is, again, look at how I'm leaving my answers. I'm leaving them as fractions. Okay, whole number fractions. Now, but what might be helpful is I am going to approximate. Y equals, I'm going to do over here approximately. Y equals, well, what was the negative 215 over 38? Let's go back up. The negative 215 over 38 was approximately negative 5.66x plus, and then my y-intercept is approximately 502-ish, 0.6. I just had a room there, 0.6. Just because if I'm comparing this to a textbook answer, okay, do you guys all see how everyone's answers here are going to be slightly different? It all depends on where you put this line because we all eyeballed it. It's not an exact science. So this line, if I shift it just a little bit, it's going to affect my slope, which is going to affect my y-intercept. This is why we like the approximately's, because as long as you have a slope approximately around that -5 range. Now, if you had a slope of positive 20, obviously your line's wrong, or you did something wrong in this process. And your y-intercept should be somewhere around that 500. Now, if your y-intercept is at 200, that might be too low. Something happened in this process or when drawing your line that goofed that up. So again, that's why we like those approximations. It's just so we can compare our answers and see, are we in the ballpark? Did we do this process accurately? Does my line really somewhat fit the data points? Okay. All right, so now that we have, this is what we call a linear, this is often referred to as a linear model. It is a model that describes the data. It's now an equation that I can use to make predictions. And when we make those predictions, we're doing something called interpolation or extrapolation. Okay, so interpolation is making a prediction using a value of the independent variable, okay, from within the model's domain. So interpolation would be my domain here is only from values from 30 up to slightly less than 198. So if I'm making any predictions about any temperature in here, I'm doing something called interpolation. I'm interpolating what's happening in here. So let's say I want to know about how many would I sell if it was 50 degrees. Okay, again, that's within this domain, my bubble of numbers right here. So that's interpolation. Where extrapolation is making a prediction using a value of the independent variable that's outside the model's domain. For example, if I wanted to figure out how much hot cocoa would I sell if the temperature was 10 degrees. 10 degrees is way down here. It's outside those domain values, so that would be extrapolation. Okay, so here we have a scatter plot and a line of fit for hot cocoa sales as shown. A shaded rectangle indicates the values that are within the model's domain. So my values domain is again between 30 and 98. So if it's between 30 degrees and 98 degrees, it's inside that domain. So that would be an interpolation. So interpolation is predict the number of cups of hot cocoa that would sell on a day with an average temperature of 80. So we could look at my data here, temperature of 80. We come up, we look at this point. It looks like it's going to be slightly more than 50. Okay. We can get even a better approximation for that. Again, we're predicting. We won't know exactly how many, but I can use the equation. We have this equation. What was our equation? Y equals negative 215 over, 38x plus, it was huge, 9550 over 19. Okay, so again, x is my independent variable, is temperature. So this is temp. And this outs up is the number of cups sold. So if I have an average temperature of 80, meaning I'm going to put an 80 in here for temp. So I need to take my negative 215. I'm going to do this all in one step. Negative 215 divided by 38 times 80, and then add 9550 over 19. I get approximately, oh, look at that. It got me a really nice number, 50. Approximately 50. And isn't that what we assumed? We assumed it was going to be about 50. So again, this is an approximation. So we would expect to sell approximately 50 cups of hot cocoa. Okay, next one. Predict the number of cups of hot cocoa that would sell on a day with an average temperature of 20. So again, now here, this 20 is we are outside the domain. So a temperature of 20, we're outside that domain. So then this would be an extrapolation. So again, same thing, my temperature is 20. This is why we like equations, because I can just plug in. So we can look here. It looks like, according to our graph, it looks like we should be about at that 350 range, maybe 350 cups. If we grab our calculator, okay, I'm just going to go up. I'm going to hit second enter. That brings back the previous problem. I'm going to come over here and change that 80 to a 20 using my delete button. And I get approximately 389 cups. I'm rounding to the nearest cup. I can't sell half a cup of hot cocoa. So we'll go 389 cups, approximately. Again, these answers here are going to be different from the textbook answers because your equation you're using, this equation you're using is slightly different, but it shouldn't be different by a lot. For example, the textbook for this one says approximately 67. We're off by about 17. Again, we're predicting. Okay, other possible answers, you could have approximately 48, depending on your how equation, so forth and so on. Again, as long as you're within, and that is a really statistic question, how close is close enough? We get into that when we talk about statistics, how far do you have to be? But as long as you're within the ballpark, you're okay. For example, an answer that wouldn't be okay, 120. Way too big, that wouldn't work. Or 16, way too small, that won't work. Okay, so here the textbook answer for 389 cups. For this one, they had approximately 347. It's pretty close. You could have 400 and some. That would be pretty close. But having an answer of 105, yeah, way too small. Or an answer of 1,560, yeah, way too big. Okay, so it has to be within that ballpark there.